go easy on delving into the details. So you have some idea of a few sampling patterns. Maybe, so yesterday in the afternoon in the lab session, many of you said you would prefer a more general sort of discussion on, because many of your PhD students, on what the opportunities are in graphics vision and what the so-called hot problems or exciting current problems are. And I think that's actually a good idea. So I think one of the things that is very hard to get an idea of is what to work on. And some of you are saying, usually you get to know these things by meeting people at conferences or talking to people. So, and some of you may not have had the opportunity to travel to some of these conferences. So maybe I can share with you my perspective. So what I would like to say is, whatever I'm going to say today about that is going to be purely my perspective, and people will differ in their opinions, but at least it should give you one perspective to start from. Okay, so the plan is, maybe first I will highlight some of the broader topics in graphics and vision. Then I will show you one particular image processing example, and then we will see what all you need. So I think, again, one of the hard things to do is to understand the problem enough to find out where sampling comes in, what sampling to choose is the next step, right? The first step is be careful. I mean, just make sure you don't step on it. That's okay. It's been around for the last 2 days. It's harmless, but it's just awkward if someone steps on it. So yeah, so what I thought we'll do is take one particular image processing problem, which is a very old problem, which is segmentation. We will look at what the problem is. So some of you may not know the problem, so I'll first sort of explain what the problem is, what the current issues are. Segmentation has been looked at for many, many years. Why is it relevant today? And what tools you might need to solve the problem. And then I'll take one particular tool that we chose, and I'll show you why sampling became an issue then. And in this sense, sampling is a bit different from what we've been talking about so far. We've talked about reconstruction and integration. And if you remember, I showed you a third one there, which was optimization. This is somewhat along those lines, even though it's not strictly pure optimization. We'll do that. And then after we do that, I thought maybe we can address this terminology / jargon thing, right, that we spoke about on the first day. So what I'll do then is throw out some of the buzzwords out there in the research community. Okay, and there'll be buzzwords in the industry as well, but I don't know them. So I'll tell you what the sort of buzzwords are, and tell you what maybe, in a few minutes, what the high-level idea is behind them. Okay? And you'll see that it's very easy to get drawn into these. So each of these things that I'll be talking about, just to name some of them, will be sort of latent variables, uncertainty quantification and propagation, some forms of optimization. Some are asking about linear and convex optimization, and all these things, right? So I will briefly tell you some of these, okay? And I can maybe show you in one or two of those cases what I worked on in terms of research and how they map to those problems. Okay, so overall it's going to be, I would say, fewer equations today and more an overview of the space. Okay, is everyone okay with this before I do this? Yeah, is this preferable to the other one? Okay, that's good. Okay, so actually, yeah, when I explained that Fourier stuff, I recalled a joke. I don't know if you know, so maybe because we're doing something lighter today, I can start with that. So there is this maths joke where there was a narrow bridge, and there was a function crossing this bridge. Okay, the function was, do you know this one? Yeah. So it's f of x equals k, right? It was crossing this bridge, and suddenly from the other side there was an operator, and the operator was told the function, move out of the way, go back, I need to cross. It's too narrow, both of us. Function said, no, I'm not moving out of the way. So the operator said, well, if you don't move out, then I will just obliterate you. Right? So the function said, how can you do that? He said, because I'm d by dx. Right? So then, okay, so the function says, okay, d by dx, I'm constant, I better not mess with him. Right? So it walks out and then comes in. Then f of x equals x comes, and same thing happens. After a while, the operator is walking along, and a function comes by and he announces the same warning. It's like, please move out of the way, otherwise I'll destroy you. That function doesn't really care. Can anyone guess why? It was e to the power x, right? So he said, you can't do anything. Okay, so then the operator says, okay, I'll go. And he moves back. And e to the power x is walking very happily. Suddenly he sees another operator, and e to the power x says, look, you can't mess with me, I've already seen you before. Then the other guy says, wait, what are you? He says, e to the power x. Then the operator announces his name, and e to the power x walks back. Why? No, it was d by dy. Right? So I should have said this when I talked about these eigenfunctions of the differential operator. Actually, it's a good joke, but I think it's much deeper than that. Right? So you understand that the eigenfunction, being the eigenfunction of an operator, is quite a significant thing. Anyway, I just randomly remembered this while coming today, and I thought, oh, maybe I should share it. Okay, so what we'll start with is maybe a chart of the space that I see as computer vision today. Okay? So what we'll do is, first of all, the main conference to look at is called CVPR. Okay, so what I'm going to give you today is some kind of clustering of the papers at that conference. If you would like to go there and see the papers yourself, you can do that. Okay, it's called Conference on Computer Vision and Pattern Recognition. But if you just search CVPR Vision, then for the more learning, people interested in machine learning, there is NIPS. So you type NIPS conference again on Google, it should be easy. Then there are journals as well. So there's a journal called Pattern. So these are where you will typically find the best or the rated papers. Of course, we don't know if they are the best papers, but these are the best rated conferences and journals for this field. Okay, so just to give you some idea in terms of timeline, does anyone know how computer vision was born? So there was a faculty who just proposed it as a summer project and said, oh, can someone solve this problem for me? Okay, that's computer vision. It turned out to be more than a summer project. And so the problems they started with were sort of very, I would say very coarsely, you can call it some of you are working on correspondences in meshes. So early on, vision was mainly focused on correspondences in images. What that means is if you have two images of the same object, in their case usually taken with two cameras like this, placed here, maybe with some overlapping areas, then the same object would appear at different image locations, right? So what they started doing is looking at patches around these and trying to identify which pixel maps to which. And of course, they had very restricting assumptions and so on. So that's sort of the main idea. And why would they need this? They use this to estimate optical flow. They used it to estimate depth from stereo images and so on. And why did they want depth? So the whole idea of vision is to understand an image with an algorithm. So when we see an image, we don't see just a set of pixels or a bunch of features. So our visual system includes processing in the brain, which interprets many of the things. Like I said, when it's dark, we do automatically filter some of the noise and all these things. So one of the big goals of computer vision is to perform this entire stretch, to do the sensing, to do the interpretation, to do the processing, and then interpretation. But early on, obviously, they were focused on very low-level operations, such as these kind of correspondences, maybe image processing, removing some of these artifacts and so on. But it's moved on. So I would say if you are interested in image correspondences, well and good. It's a very interesting topic. You will find hundreds of thousands of papers on this. It may be less exciting for the community. So even if you come up with a reasonably good correspondence, community may not be that excited, and if you still want to do it, that's fine. So that's sort of where it started from. And then so there was this optical flow for motion. There was sort of stereo and depth and all that stuff. And you can see this, I would say this is at least 40, I don't want to commit to a number, but it may be 40 years old. But if you see today, this is very relevant for the industry. Many of these cameras that come out today come out with two cameras on the phones. And what they would have is something like this. These two cameras, mine only has one. But in front, if you have two, then it's going to take two images like this. And they want to get depth. Why do they want to get depth now? Because when you voice chat, if you have your depth image, then they know you they can know your face in 3D, and then they can manipulate it, and you can add all these fancy effects and so on. So even though it was actually explored as an academic problem and then found out to be useful in academic research for various measurements and so on, there's now a very widespread sort of commodity usage of this stuff. So yeah, so it takes a while for academic research to do this. Anyway. So if, in terms of industry, I think it's very relevant. If you can find fast algorithms for this, if you can use low memory, low computation, and the big buzz now is low power. So if your algorithm consumes low power, then mobile devices, mobile companies will just, offer you a job straight away if they know you can solve it. Okay, so that's sort of where they started, right? And then I think people started asking slightly higher level questions like, segmentation. Okay, so here, segmentation is the problem of you have an image and you want to identify where the person is in the image. Okay, and this is different from simply object detection. When you do object detection, what happens is, so perhaps object detection came first. Right? So for object detection, if you have a human, object detection will say found a human. Segmentation will say the human is these pixels. And there's a slight difference. And to do both of these high-level tasks, what the underlying thing you may need may be classification. So this is widely used in computer vision. Obviously, classification is a machine learning concept, and it has been around even before machine learning. But this classification took appeared in different applications like detection, segmentation, and so on. Again, if you can do good segmentation, you're very useful to industry. Okay, in academic research, I think segmentation is not considered exciting now. My view, it is not solved. So the state-of-the-art segmentation algorithm is very good, but does not work robustly. So if we give it some example, so most people assume that all this stuff is solved because in academia, I think you may not, reviewers of papers may not find it super exciting. Okay? And that doesn't mean it's not good work. I'm just telling you, so if you get into this area, be prepared for reviewers coming back and giving you little complaints here and there. It's mainly because they think segmentation as a problem in academia is not that exciting. However, if you find a good way to solve it, then I think it will excite them. So if you do incremental stuff by tweaking older methods, they may be less exciting. That's my word of caution about any of these older things. Recently, I think this has, again, there was a surge. So I think this whole middle period, there was a lull because people were doing these sort of small changes, finding these. And then there was sort of a period when this became prominent. And then again, there was a lull for a few years. And I think over the last few years, there has again been a spike, even more than there. This spike was when classifiers improved and machine learning was starting to catch on, I would say early 2000s, when the vision community started adopting many of these methods. So you had various sort of tools, like what do we say? So for example, random forests. I'll just put all this stuff here and you can look them up. There was, do you remember the other one they, no? Yeah, support vectors. What is it? SVMs, support vector machines. Yeah, SVM, that's the one. So SVMs and things like that, right? Then it became suddenly sort of, oh wow, this is good. Then after a while, people were like, yes, so it was useful. They found that between when they did it here and here, suddenly things were working very, very well. And then there was sort of a period when people became less excited because then people started tweaking random forests, SVMs, combining them with older methods and all that stuff. So the industry here was very happy. They started adopting many of these things, but in academia, again, there was a little drop. And then what happened was here, there was basically, I think it started with radial basis functions. Then there was Gaussian processes. I'm just putting all the buzzwords at the bottom. Okay, so as these came along, they created a new sort of toolkit. And people who were doing standard image problems started using these and found them to be very powerful. And also this was the time when data started appearing. So a lot of this data was being used and it was exciting. Because so far, segmentation was, I should tell you, the computer vision people, at least historically, were firm believers that we should not have a human in the loop. Okay? They always, from an academic perspective, their ultimate goal was that the machine will solve that problem. It will identify something, segment something, reconstruct the depth or whatever it is without any human intervention. However, they found that with these tools, it was quite hard. With these tools, suddenly it became slightly better. And here, they found a nice sort of convenient loophole, which is instead of using human to say stuff, they said, we will train the machine with data. Well, actually, if you think about it, how did they get the data? There was a human telling it, look, this is a segmented boundary, this is a human, this is a car, right? So in some sense, that is fine. That's what we want. That's what is useful. But I think it took them about 60 years to acknowledge that, yes, these things are useful and we should use them. But I think their bigger point is that they didn't want the human in the loop. So they were happy with databases, but they were sort of, I would say, apprehensive of getting a human in the loop while you do the segmentation. In contrast to the graphics industry, which realized, so for example, in movies, they've been used for a very long time. Because even before CG, people had to hand draw these masks on photographic plates and so on. So even Disney, Walt Disney, during the animations, they had these kinds of techniques. So in graphics, people took the approach that, look, if you think you can solve the problem more effectively by asking a human to do something, by all means do it. Okay, and that's how Photoshop and all these things are prominent. Is now artists, so these film companies will give a scene and they will say, oh, look, there are cables because the actor is using all these suspended by cables, and they'll say, just shade out the cables. So they will send it to somebody. There'll be a bunch of artists. In fact, so around this time, when these things became prominent in computer vision, computer graphics people moved to a completely manual setup. Actually, they were shipping some of these companies film reels to India. They had several, so many of the big animation houses, even today, they have pretty substantial units here. And there were people in there who would take, 24 frames a second, 5 minutes is 120 frames, right? And they would take every single frame and erase the cables, right? Or they may segment the human with a device like what I'm using now. Okay, so they were skilled artists, and they were doing this on a daily basis, so they were very good at it. And what they found, these companies found, was that using all of this stuff was not a guaranteed result. They would do all this stuff, and there'd be a bit of a cable showing somewhere. And it was really, quantitatively, the computer vision community, again, would say, oh, the MSE is less than 1E minus 6. And nobody cared, right? You can say whatever you want about the MSE, but if I see a shining string there, if the audience sees it, the movie is not going to fly, right, literally. So they said, okay, we cannot accept this. And so they just moved to a completely manual mode. Around this time, when this became prominent, the computer vision community took some of these tools and started helping artists. So instead of having them to painfully paint every little detail, they would take some of these tools and then feed them to the artist and suggest. So you'll find a whole range of papers in graphics conferences on suggestion-based. So they had various ways where, as the artist was drawing stuff, they would display some suggestions to him or her, saying, can you take this into account? So there was a lot of work in graphics, and they found that was working very well. Because now artists could only paint the first frame, the middle frame, and then generate all the intermediate. And then they would just go through them to make sure it was okay. If it was not okay. So that was the graphics side of things. On the computer vision side of things, they said, look, this is not acceptable, this thing, because all error and all of the stuff, how you measure or validate the algorithm depends on the skill of the artist and the particular scene they're doing, and so on. Oh, why is it locking so soon? So yes, they said, look, this is not acceptable. And they came up with this idea of using data that has already been collected. Okay? So this bit here suddenly saw classification took sort of two main: supervised learning, and before that it was mostly unsupervised, right? So there was some development in unsupervised as well. And now there's something called weakly supervised. This is a very hot research topic. There are many colleagues working on this. And one of my postdocs also working in that area. And it seems to be something that the vision community actively wants to improve. I'll tell you what these are briefly. But yeah, so the key thing here was suddenly they would take a data set of million images. So there were many of these. Google has some. There are many publicly available. So you can go up and download them today, which just showed millions of images and had human labeling. So each of these images will have classes for every pixel. Each pixel will be labeled, for every pixel. So example, that pixel, it will say car. This pixel, it will say plane. This pixel, it will say road, and so on. Okay? And using those labeled pixels, they went back to this patch approach initially. They said, okay, that pixel is a car. We will look at the patch around it and then give this machine learning algorithm this piece of information. So they would give the algorithm information that this pixel is a car. So that is the right side, right? They would say patch equals some function, car equals some function of this patch. Tell me what the function is. Because if I can learn the function, anytime I have a patch, I apply the function, it will tell me if it's a car, plane. Right? It was not a function really, but I'm just trying to, it was some kind of space where they were classifying. So they were taking these data points and then trying to identify the clusters or the boundaries. Yeah, so that took off, and the more images they used, the better they could get, and then people improved all these methods. methods, and they didn't. So this patch-based thing went to a more general feature-based learning approach, and then people started asking what features are better. When I say feature, this is a feature, it's a patch, not a feature like we would think. So when I look at you, I may say, as features, I identified eyes or top cap of a bottle or something like that. But these are purely pixel-based features. Right? So there's no semantics yet. The semantics are what humans have provided in the data set. So that was the next step. People went from patches to more general features. And then they looked at Fourier transforms, wavelets, all these kinds of frequency domain representations, which were just feature definitions. So a lot of people made their career in this period on proposing features. And it turned out that some features worked really well. And when that happened, this started going down again. Right? People were like, okay, we kind of know now what features work well. And we have too many features in the phrase, so we're not really sure if this is useful anymore. Right? This is exciting anymore, sorry. It was all useful. They're not sure if they were excited by it. And then what happened, video came along. And similar things were repeated for video, and it's a harder problem because you have time domain and so on. Okay, so that's sort of the history. Okay, so what is exciting now? I think what people consider exciting now is, so one, this weakly supervised business, right? So in this, the main idea is you've given it some training, and then you have some way to evaluate whether it's good or not. And you have the algorithm repeat. Using what it deduces, you have it supervise itself. Okay, so it basically augments the training data with some other algorithm, and then trains itself using it. Okay. And of course, the more general form of this is reinforcement. Right? So RL. And that is, so that's a course that we teach at the master's level. Learning. And it's, I would say as an idea, it is not very new, but people are just starting to understand how to use it, how to harness its power. It's a very powerful idea. Has anyone heard of this or followed this in the news? It's only one or two of you. Yeah, I was going to do that next. Because transfer learning is a higher level concept. These are sort of telling you how to learn and transfer. Yes, so I'll come to that next. But let me just tell you a brief story about history learning. RL, reinforcement learning, is this game. So have you seen this game like bricks, where you have bricks here? I mean, it's a very popular game, right? And then you have a ball that drops, and you move this paddle left and right, right? So one of the things that brought RL into the news was what some people did. So they said, look, one of the ideas we want is to remove the human from the loop. The second is we don't want to rely on semantic information. We don't want somebody to tell us that is a brick, this is a ball, or whatever. Whether it's an algorithm or not, we don't care. So actually they tried something that seems, I mean, almost like science fiction at that time, it seemed. They took the pixels in the image. Like we've seen, you can take this matrix and just write it as a vector. They took the pixels in this image, opened it out as a vector, and started doing random perturbations here. So they took this paddle, and they let the ball drop, and they moved it right by some value, arbitrary, random value. The ball dropped. Random direction, random amount. Right? So totally randomly, they just moved this. Obviously, the constraint is, so what they know is that there are two inputs to this system. Or, yeah, there is You can either move left or right. And that was why they chose this, because the only two inputs you can give the system are these two, right? The whole game revolves around how you use these two. So what they did was they randomly chose one or the other at every time frame. Okay? And what they observed was the reward. Well, so actually the interesting thing was, I think later they didn't even tell it. So you know there's a score here, 88, 100. What they gave it was some virtual reward. Like every time it knocked a brick, they assigned a reward. So so now there's a lot of work on how do you learn the reward. But let's say you come up with some reward every time something favorable happens, like you knock a brick or multiple bricks. You can do that by difference imaging or something like that. And they just let the system run. That's it. And they said, whenever you see that you're moving towards a higher reward, remember that's a useful solution. Very high level description. So they just let it run for a period of time, and without telling it anything about this image structure, right? They just had this image as a bunch of pixels. The algorithm learned that when the ball is here, depending on where the paddle is, you need to be left or right. Right? So they didn't actually give it this, because this would cause the same problem that Vijay suggested that day with linearization, in that once you open it like this, you don't have this proximity structure and so on. But it turns out these learning algorithms are very good at dealing with images, right? So if you've heard of CNNs, so yeah, maybe that's another word to add there, right? So the CNNs are very good with images. So now if you forget about this and think of just the raw pixels that they gave these as input, and the output was this, and was also given a reward function. And the algorithm sort of, the goal of the algorithm was to maximize the reward. And of course, now you can think of many types of reward. Do you want the maximum reward during the gameplay to be the highest? Do you want the integrated reward to be the highest? So you come up with different metrics, right? So that's what the RL community works on. What are the relative advantages and disadvantages of this? So this is a very high level view. Now, if you go in one level, a little bit deeper, you start asking questions like, can you give it multiple rewards? Can it learn the reward? Do you integrate the reward and all of that stuff? So the RL community looks at a lot of this. And they already have some tools that we can just use out of the box. Actually, one of my PhD students, I don't know anything much about the research in RL. She just used this out of the box. She opened, in fact, just yesterday, she had sent me some results. And it's quite a hard thing to debug, because it's doing a lot of stuff in here. And if it works out of the box, well and good. But in our case, it's working okay, but it's not what we want. So now to debug this is going to be really painful. Like she's very, so she took the course and she knows all this stuff, but opening the box and changing things is totally different, because I think even the community doesn't have a very firm grip on how to change things and so on. So yeah, that is a very active research area. Okay? Yeah. So then there was mention of transfer learning. If you remember, one of the slides I showed you on the first day was this robot pouring a liquid. And then I said the recent thing that we're trying to do is, instead of learning by pouring, we're learning by stirring the liquid. That is nothing but, you can think of it as transfer learning. There is some debate in the community because there's something else called domain adaptation. Okay? And people may disagree about whether, in fact, we had this discussion with people in our department, and some of them thought it was transfer learning because we learned how to do something with like this and then transferred it to a different task. Others claim it was just domain adaptation, that we went from rotation-based stirring domain to an angular-based. So instead of this angle, it became this angle. So they claim it is just a change of domain. It doesn't matter. The point is they're quite close. And sometimes it's very obvious that your problem will fall in one or the other. But many times you could interpret it both ways. And there are many tools. And again, I would not say that people have fully understood these things. So again, it's a great area to start your PhD in. or even a postdoc. Right? It's a good area to look at. So that is domain adaptation. Then I'm forgetting one more, right? Yes. Yeah, so then, sorry? Yeah, so deep net, so yeah, so of course, that most of you know, right? Right, so that's a tool. So all of these things that I'm describing are methodologies. Okay, so if you look here, so these are tools. These are tools, but these are all methodologies, right? These are approaches to how you might solve a problem. And you can take the same problem and you can solve it using many of these approaches. And that is actually what happens in the research community. We go to look at CVPR. One person will pose the problem of, segmentation as weakly supervised. The other one will pose it as reinforcement. The other one, third one will pose it as. Some problems map more elegantly into one of these. Some you may use two different methods. And so the goal of academic research to understand what the advantages in research in that area is to understand what the relative merits and demerits are. Yeah, so deep networks, again, very powerful tool. People use deep nets to do all of these. Okay. But you can also do all of these without deep nets. And so the robot project that my student worked on, we did not use deep nets. And we found that we were getting some idea. So when we started, we didn't want to use deep nets because it's hard to understand for us. Some people understand it very well. So we said we'll start with something we understand, so we use classical sort of Bayesian optimization. I'll come to that later. And then said, okay, this year said, okay, we'll try deep nets and see if it makes a difference, and it does. So it has improved things a lot, but I think if we hadn't done that first step, it would have been very hard to know what to do with the deep net. Because we took that simple approach first, when we dropped the deep net in, we had some idea of what we wanted to achieve with it. For some people, like some of my colleagues, they know this stuff inside out. And I think till recently there was a criticism that nobody understands them. But I have met people who understand it very well. So I think there are a few people in the world, maybe a dozen or so, who understand this really well, which already says that it's something quite hard to understand. And I think they have intuition about it. So just like the reinforcement learning learned this, what they have done is they have looked at deep nets behaving in different ways. They've been giving it different parameters, and they have learned something in their heads, right, with their neural net, how to control this or what the thing should be. And they had their reward function because they knew what they wanted to achieve. So just by virtue of experimenting, and many of these guys have large armies of PhD students. They have 10, 15 students, maybe 3, 4 postdocs. And what they've done through this, what you could argue as being very valuable to the community is they've used these large groups to train their own neural nets to understand how all these things work. Unfortunately, I think very few of them are able to communicate to other people why or how they work. So they've built this whole thing, and they have, I think, the same problem that nets have, is that once it has learned something, we cannot easily understand what it has learned. And I think people are similar in that these guys have learned how these things work. So at the next level, they're not able to tell us. So some of these guys are actually friends of mine. I know at least a couple of them who understand it very well, and I go for lunch maybe 3 days a week with them. And they are not able to explain it to me in a way that I understand. Okay, I understand how things work, but I don't have the intuition. Like if some of them, when they listen to our problem, they'll be like, oh yeah, you need to add this. This is how you need to connect them. This is the optimization you need to run. And when we try it, it works reasonably well. Okay, but there's no way we would have randomly come up with that. Which means, so one interesting idea that I have now is to come up with random CNNs. And people have tried this, but remember all the sampling approach. I'm wondering if you can take these CNNs to be this kind of problem. randomly generate, I don't know if you guys know the details, you can randomly generate these layers and the connectivities. So the topology of this network, let's say you randomly generate one, and then you train it. How far off will you be from this hand-tweaked solution? That is essentially a question that some people are looking at. But I think I would be very keen to try them out because I understand something about randomness that maybe those guys have not looked at. Right? So many of them come from probabilistic background, but they come from a slightly different mindset. So I'm curious to do this. So if any of you is curious, that'd be great. We can chat about this. Anyway, so that's in summary, right? So this is what a lot of the vision community focuses on. However, I must say that the guys who are doing sort of next generation vision research, in my opinion, are using all of these things as tools. So I think there's been a big shift in computer vision recently, is that they moved from image acquisition, image processing, image manipulation, image understanding. So this is just my own sort of chart to image interpretation. And I think this is where, if you are thinking as a young researcher, I think this is where there is a lot of interesting stuff to do. So to give you some example, you can imagine acquisition is the whole process of just taking the image. Processing, I think most of you would have taken courses. I saw a book someone was reading where you're doing pixel level manipulations of the image. You're trying to remove objects, place objects, completion, segmentation, noise, denoising, all this stuff. Okay, that's great. But I would think in the computer vision sort of timeline, it is second generation. Second generation, my view. Okay, so what happens is I think institutes that are, or researchers, like especially young researchers in parts of the world where they don't receive funding to travel to CVPR and all these conferences, unfortunately don't realize that it was almost 3 generations ago. It's still very exciting. We don't know many things, but actually there's a lot more exciting stuff as well. So if you're thinking of image processing, I would encourage you to, yes, think about it, but also look at what else you can do. Okay? And I don't mean to change your focus, but I really think this has very, very interesting observations and research topics where you can use your understanding of image processing and all these other tools I showed you on the previous page to actually advance recent sort of results. So to give you an example, so image manipulation is what I talked about, like where you have these artists removing wires. Maybe you want to, so there was another very applied problem in image manipulation was you have an image that somebody has shot, let's say a movie. Now, if someone is watching it on a cell phone or on a different device or in an airplane seat, you don't want to show the same set of pixels because their conditions, viewing conditions are different, the aspect ratio of the screen is different, and so on, right? In that case, what do? You can't simply squish and stretch this, right? Because then it looks ugly. So the question is then, how do you remove pixels? So in image manipulation, one of the very hot problems maybe about 8 years ago was, 8 to 10 maybe, was how do you transfer these images to different formats for different viewing conditions. Right? And this was called image retargeting. And that is an image manipulation example. And then people move to image understanding. So you've probably seen Google's result where they took a photo of some guy throwing a frisbee. Has anyone seen that image? Yeah. And Google's auto captioning says, man throwing frisbee. So it's able to interpret this image based on training enough to give us a caption. And this was auto captioning. That example was auto captioning. And this is not very old. When was this? Do you remember? 2015, 13, okay, 14, something. Anyway, in the last 5 years. Okay, and this again, people haven't solved this problem. So I'm not saying people have solved any of these problems. By the way, people have looked at them for long enough that they have found more interesting problems. So, and they haven't solved this problem, but there's a lot of stuff to do as well. And this image interpretation is somewhat similar, right? With the very slight difference that here you're given an image and you're asking some fixed questions about it based on some training data. And in interpretation, you are attaching this question as to this. So now you're asking a question like, why is he throwing the frisbee? Okay, now this starts getting into grounds where we're not comfortable as researchers because we don't know that there may be a known reason. Only that person throwing the frisbee probably knows that reason. But as humans, we are able to guess many things. So we are able to understand why people are doing certain things. If someone's crossing the road, we make a reasonably accurate assumption that they want to get to the other side, right? And this will not give you that. It will simply say man crossing the road because it has seen many images with a man. It has seen many images with a road, seen many images with a man on a road, which have been labeled man crossing road. So it knows the words man crossing road and somehow puts them together. Okay? It does not make any sort of attempts to understand this image in terms of a goal and interpret why they're doing. And this is very relevant today because it also refers to predictability. So it will maybe then help you understand things like what they may do next after they threw it. So what this will tell you is if that's the image, then that may allow you to predict that maybe the arm will come out like that, right? Whereas this question will allow you to predict that after throwing the frisbee, maybe the other person will catch it or something like that. Or maybe he has something else. And so I can't think of a suitable example, but you can imagine that there are sequences of actions that we do regularly. And unless we know why they're doing something, there may be a branch structure. So for example, I may do action A, and then I may do B, C, or D, depending on why I did A, right? And so if you know why you did A, then you will know that the next action is B. And that's, in terms of a prior, there's a very good prior for human behavior. So whether it comes to, transport simulation where you want to know, somebody was saying yesterday, I think Abdul was saying, you may want to know why a driver is doing something, what they're doing from images and so on. This is very relevant. Also in terms of understanding physics, like for example, in that case where we were pouring water, we wanted to ask questions like, why is there spillage when you turn at this velocity, or things like that. But in that case, we had the physical model and all that, so we didn't worry about doing it from an image perspective. So there are many reasons why you may want to ask such questions, and there may be many ways to deduce the answers to them, but one of the ways that you might do it is with just images. In that case, computer vision comes into play. And then this image interpretation becomes an important topic. And I would say this is very, very new. Okay, there are 2 or 3 groups. As far as I know, they're working on this. So one is this MIT group with two guys. It's more Freeman. Bill Freeman. Bill is William Freeman, and Ted Adelson. And then there's some guys in Stanford. I forgot it. Yeah. Graphics, yeah. So I haven't mentioned graphics because I'm going to talk about graphics next year. So I'll bring graphics in next. But that's very true, right? And I'll say why graphics is important for vision and why some of the vision people in our department use a lot of computer graphics as well. Okay, yeah, so this is another very trending field. Edinburgh, where I am, has apparently one of the, I would say, top 2 groups in the world for this. So if you want to get any contacts, I'll be happy. You just email me. And if you want to work in that area, a lot of these people in our department are always looking for postdocs. So if you've already got your PhD, I would say look out. And so there's a slight thing in the UK. There is very limited funding for Indian or any non-EU PhD student. So I have a lot of funding, but I'm only allowed to recruit with that EU students who are in Europe, in the European Union. However, for postdocs, there is no restriction. And there are a lot of people with money not able to find good postdocs. I'm sure the problem is everywhere in the world, including here. But for us, that is sort of extreme in that there are, I don't remember how many researchers, but at least 3 researchers in that group who have ERC grants. They have ERC grants, which are really massive grants. And many of them have like multiple, because the government is actually actively funding this very heavily. So they have loads of money. And I know people who are looking for like 6 postdocs on a project. And there are at least 3 or 4 of these kind of people. So there are so many postdoc openings. So you have to apply to them if you're interested. But before you apply to them, and I think this is why it's relevant to you. I mean, if you're close to your PhD, it's not relevant because it'll take you a while. But if you're in the middle of your PhD, then maybe whatever you're doing might have some possible connections to these, or you can study this on the side so that when you finish your PhD, you can apply to these groups with the appropriate skill set. If you simply tell them, look, I'm doing work on this, and it's completely irrelevant to their work, then they may not interview you. So it's a good time. If you're in your BTech, that's even better. It's a good time to start reading up about all of this stuff. Okay, so I think I had planned to do one more thing before the break, but we can do that after we're back. Or do you want to do it now? Now? How many of you want to do it now? Okay, most of you. Okay. So I'll quickly show you. So so the connection between graphics, we will do it after the break. I'll quickly show you one example of why sort of these things bring sampling into the picture, right? So this was an old paper from 2013. And here's the segmentation problem, right? Somebody gives you an image like this, relatively easy image to segment. Why is it easy? Huh? Large, no. I mean, the segmentation means you have to segment the leaf, not the box. Why is it easy to segment the leaf in this case? Focus. The leaf is in focus, this is not in focus. So if you work at a pixel level, this is a very hard problem because the colors here and the colors here are very similar. You may not know which one is this. If you look at patches, maybe you will identify a coarse boundary. However, it seems like it should be a fairly easy task, right? Anyway, we're just doing this to highlight that the segmentation result may look something like this. Actually, you'll be surprised that it's very hard to do this with current tools. Okay? I say current, I mean like 4 or 5 years ago. And we may want to do this because we want to replace the background. And most Indian movies do this, by the way. At least South India, I know all the movies, they do this heavily. What they do is, even if they don't change the background so drastically, when they shoot in India, because of the dust and things and the pollution in the air, even in forests and so on, there's a lot of haze in the back. And water in the lakes and so on doesn't look as vibrant because the sun is too bright. So what they try to do is, good directors shoot at appropriate times of the year and lighting times and so on. But many of them can't afford that. They get call sheets from that. So what they do is they just go out in the field, record whatever, then they segment out whatever they need. For example, especially dance sequences and so on. And then the background, they will just boost all the colors. Right? So once they have segmented it, they will just take this background and boost all the greens to make the trees look green, boost all the blues to make the water look blue, and so on. So in some, you can really see it's jarring. You'll see this really bright blue in the background, which is very unnatural. So that is a very, very common operation, and there are many, many tools to do this. And one of the things the graphics community was interested in is how can we do this with some sort of user indication. So rather than training based on hundreds of images before, we just take one image and we ask the user to maybe say that is foreground, that is background with some coarse indication. Right? And then based on that, we would like to get this. And the problem is you may get overlaps like this, and you may not get a good segmentation. For example, when the color blends in. And these things need to be manually retouched. Right? It's quite tedious. This is even more relevant because today you might want users to do this stuff on devices which have very high resolution. So if you take a iPad, the resolution is insane, right? What is it? Is it some 3000, some 4000, 4K, right? But in the end, if you look at the input device you use, it's your finger. So every time you touch the device, maybe you're touching about 500 pixels. Okay, so there's no way you're going to be able to segment this at the pixel level. Even if you zoom in, it's very hard. So precisely giving this input is very, very hard. But we can do very coarse input. Like, for example, if this is the thing we want to segment the leaf from, we can maybe say, look, there's a leaf here and there's sky here. The problem then is we may be inaccurate. Even though we will say this is the leg of the ostrich, when we do this, we may touch a few grass pixels. And suddenly that algorithm will get very confused because you're training it with the wrong data. You're telling it ostrich leg, but you actually touched a grass pixel by mistake. So what we looked at is how can we accommodate user error? Because most machine learning algorithms assume that the supervisory input is accurate. And the minute you deviate from that assumption, you don't really know what's going to happen. So we wanted to look at robustness. So we said we want to make sure that if the user is not accurate, then you will get some. So for example, in this penguin image, what we thought was it would be nice if you simply did this to say, look, the penguins are here, this is my foreground, and that's my background, right? No other input is given to the algorithm. So it doesn't know that penguin, it has not seen any prior supervised training data or anything. It's just one image and these two strokes. And as you can see, from a color perspective, it's very hard. There's shades of yellowish white here and here and here. There's black here. There's grays and blues everywhere. So just from a color perspective, it's very hard to get this. But the result we get looks something like this, which is fairly pixel accurate. And so what we did was we formulated it as a labeling problem where we said every pixel here, like we said before, we'll give it some probability distribution. This is not a PDF, it is a PMF, probability mass function, because we have a finite sort of number of classes. In this case, foreground, background, and unknown, or could be either. So we had said, look, this pixel is most likely background, but there's a probability that it could be foreground or unknown, for example. And then, as the output, we are asking the algorithm, label every pixel as either foreground or background. And the question was how to do this. Okay, I think that's a good point. We'll break here. And then when we come back, I'll show you why sampling is important.